Hello guys, I'm Harshith of branch ISC currently studying at Sri Venkateswara College of Engineering. Today I'm here with another topic called dynamic hashing and leftist trees belonging to the subject data structures and applications. Introduction to dynamic hashing and leftist trees. Dynamic hashing is a technique used for efficient data storage and retrieval. Leftist trees are a type of binary tree that prioritize balancing during operations. Combining dynamic hashing and leftist trees can enhance performance and optimize memory usage. And here is the example for the hashing data structure. Dynamic hashing overview. Dynamic hashing is a technique that allows a hash table to dynamically expand or shrink as needed. It eliminates the need for rehashing and reduces collisions. Dynamic hashing uses a hash function to map keys to a specific location in the hash table. As here mentioned, hash table in data structure. There is a key 1, key 2, key 3, key 4, and so on keys n. When the keys move on with the hash function, when they solve the hash function, they they get a index value, and the index value will be arranged on the basis of the index present in that table next to it, and the value will be assigned there, assigned in the places of value 1, value 2, value 3, value 4, and so on. It's how the hashing function works. Key features of dynamic hashing: splitting, coalescing, directory. Firstly, splitting. When a bucket becomes full, it is split into two new buckets. Coalescing. When a bucket becomes empty, it is merged with its neighboring bucket. Directory. A directory structure is used to locate the appropriate bucket based on the hash value. Dynamic hashing, good for database that grows and shrinks in size, allows the hash function to be modified dynamically. Extendable hashing, one form of dynamic hashing is is called as extendable hashing. Hash function generates values over a large range, typically b bit integers with b is equals to 32. At any time, use only a prefix of the hash function to index into a table or bucket addresses. Let the length of the prefix be bits. Bucket address table size is equals to 2 power I. Initially, I is equals to 0. Value of I grows as the size of the database in grows. Multiple entries in the bucket address table may point to a bucket because our actual number of buckets is lesser than 2 power I. The number of buckets also changes dynamically due to coalescing and splitting of buckets. Leftist trees overview. Leftist trees are binary trees that prioritize balancing during insertion and deletion. They ensure that the left subtree always has a greater or equal height compared to the right subtree. The leftist property allows for efficient merging of two leftist trees. And here is the example for extended binary tree with, with a where leftist trees is also used. Number of external nodes is n plus 1 in the leftist trees, where where the leftist trees become greater when compared to right side. Key features of leftist trees: leftist property merge operation Efficient insertion and deletion. Leftist property. The left subtree has a greater or equal height compared to the right subtree. Merging two merge operation. Merging two leftist trees results in a new leftist tree with balanced height. Efficient insertion and deletion. Leftist trees maintain balance during operations, ensuring logarithmic time complexity. A leftist tree length of rightmost path is 2 and the leftmost path is 1, 2, 3, and 4. Advantages of combining dynamic hashing and leftist trees. Improved memory usage. Dynamic hashing optimizes bucket sizes, reducing wasted space. Efficient data storage and retrieval. Leftist trees ensure balanced search trees for quick access. Reduced collisions. Dynamic hashing minimizes collisions, enhancing overall performances. Use cases for dynamic hashing and leftist trees. Database systems. Dynamic hashing and leftist trees can enhance indexing and query performance. File systems. Efficient storage and retrieval of files can be achieved using these techniques. Caching management. Dynamic hashing and leftist trees can optimize cache utilization. Hash table in data structure, key 1, key 2, key 3, key 4, and so on, key n performs a hash function and indexes the value in the index table. Implementation considerations. Choosing the right hash function, designing efficient merge algorithms, balanced trade-offs. Firstly, choosing the right hash function. An effective hash function is crucial for dynamic hashing. Designing efficient merge algorithms. Efficient merging of leftist trees is essential for performance. Balancing trade-offs. Balancing memory usage, access speed, and operations complexity. And key, where key 1, key 2, key 3, hash function, there is a hash function, and hash table where the index and the values are present. Components of these are the components of hashing. Example application: database indexing. Dynamic hashing can be used to efficiently distribute records across multiple buckets. Leftist trees can optimize the search and retrieval of records within each bucket. Combined, they provide efficient database indexing for quick data accesses. And the conclusion, dynamic hashing and leftist trees are powerful techniques for efficient data storage and retrieval. When combined, they can enhance performance, optimize memory usage, and minimize collisions. Understanding their features, advantages, and implementation considerations is crucial for successful application. Computing frequent item sets. Given the set of candidate item sets CK, we need to compute the support and find the frequent item sets. LK, scan the data and use a hash structure to keep a counter for each candidate item set that appears in the data. Transactions and the hash structure. uh, TID where the numbers are present 1, 2, 3, 4, 5 items are bread, milk, bread, diaper, beer, eggs, and so on. There are 5 items. There are 2 items, 5 items, and many items in the but the numbers are 5 and the hash structure in the buckets it must be arranged in a proper way. It is called as hashing. And the bread and the milk will be separated and stored in the separate buckets. It is called as hashing. The separation, the easily identification of uh, of the things. Like we can find the any of the identify numbers which should be identified easily when we go through hashing functions. And thank you guys, it's been my video. uh, Please like the video, and thank you for watching till now. It means a lot. Thank you so much guys, thank you.